and welcome to Code Disclosed. In this video, I will explain the idea behind Taylor series or Taylor expansion, how to calculate the terms of this series, and then how to code it using MATLAB. So let's start first by introducing the definition of Taylor series. So Taylor series or Taylor expansion of a function is an infinite sum of terms that are expressed in terms of the function's derivative at a single point. Now, this series or this expansion was firstly introduced by Brooke Taylor, the English mathematician Brooke Taylor. And since then, Taylor series is regarded as an awesome concept, not only in the world of mathematics, but also in optimization theory, function approximation, and machine learning. It's widely applied in numerical computations when estimates of a function's values at different points are required. So to put it into math notations, this is what the Taylor series looks like. So as we said, Taylor series is an infinite sum of terms. So I have n equals 0 to infinity, and n here is the represent the derivative of the function. So it's infinite sum of terms that express in terms of function's derivative. So n here is the derivative. When n is 0, then you take the 0th derivative. N is 1, first derivative, n is 2, second derivative, so on and so forth. At a single point, which is a, and this single point can be any value, any real value. So let's expand this. So if I want to expand this, let's start with n equals 0 here. If I take n equals 0, then I need to evaluate my function at that point, f of a. All right, what if n equals 1 in this case? Then I need to take the first derivative, and then divided by 1 factorial. All right, let's put n equals 2. Then I have 2 factorial here, but I need to calculate the second derivative of my function. And then x minus a, here I have n2, then it's x minus a squared. And then I have to carry on with adding terms. It's an infinite sum of terms. All right, I think it would be better to apply this to an example to elaborate or to explain that even further. Let's say that I have a function, f of x, x cubed minus 10 of x squared plus 6. That's my function, and when I plot it, I'll have it just like this. This is my f of x. And I want to expand this function using Taylor series at a point which is a equals 3. All right, so let's put the definition of Taylor series first, and let's put the terms. So this is the first term, f of a. This is the second term, the first derivative of a times x minus a, second derivative, third derivative, plus infinity. Now, realistically speaking, I can't carry on with adding terms or calculating terms infinitely. I need to truncate at some point. I need to truncate this. I need to stop at some point. So, but if I need to stop, this equal won't be there anymore. It will be an approximate in this case. So my Taylor series will give me an approximate of the function, not the function itself, but a very close approximation to my function. All right, so in this case, I'm gonna just calculate the first term, second term, third term, fourth term, and I'm gonna stop. And then I'm gonna ask, would that be enough? Do I have to keep adding? Do I have to keep computing terms, or I just got a very good approximation of my function? All right, so let's start with the first. Let's start calculating the first term, and then let's add it back to the series. So the first term is f of a. F of a means that I have to take my function and evaluate it at a. So instead of each x, I need to put a instead. A is 3, then it's 3 cubed minus 10, 3 squared plus 6. Just very simple math operations. I will get minus 57. Let's put this back into the series. So the first term of the series will be minus 57. All right. Let's ask the question, will that be enough? If I plot this minus 57 here, will I get something very close to my function? Well, if I plotted this, I will get just a line, which is way far from the function. So I need to calculate another term. All right, so let's calculate the second term, which is the first derivative of a times x minus a divided by 1 factorial. All right, so let's calculate this bit first, which is the first derivative. Let's take f of x and derive it one time and then evaluate it at 3. So if I want to derive it one time, then it's 3x squared minus 20x. And let's evaluate it at 3. Then instead of each x, I need to put 3 instead here. And just by calculating this, I will get minus 33. So this minus 33 is just this bit here. So at the end, I will get minus 33 over 1 factorial times x minus a. So if I want to put it back into the series, then I have the first term, minus 57, and the second term, which is the one that we just calculated. Let's ask the question again. Would these two terms give me a very a good approximation to the function? All right, let's plot it. Well, still no. This is both terms actually, and still we are way far behind getting the approximation or an approximation for that function. All right, let's carry on. Let's take the third term, which I need in this term to calculate the second derivative of that function. Calculating this second derivative will give me 6x minus 20. Evaluating it at 3, I will get minus 2. And this minus 2 is just that bit. So let's put this back into the Taylor series, that this is minus 2 that we calculated over 2 factorial, which is 2, times x minus 3 squared. So here we have 3 terms. All right, let's plot it and ask the question if that would be enough or not. All right, well, these 3 terms, they look like this. I'm still far behind. I need another one. All right, let's carry on with the last, with the final term here, which we need to calculate the third derivative. I'm going to do exactly the same thing. I'm going to calculate the third derivative of this function. Will give me just a constant actually, which is 6. Evaluating it at 3, it will remain 6 actually. Okay, if I want to get 6, so this is 6 here, divided by 3 factorial. So 3 factorial is 3 times 2 times 1, which is 6, times x minus 3 cubed. All right, so I have 1, 2, 3, and 4 terms. What if I plot these 4 terms? Wow, so if you can see here, just by adding these 4 terms, I get very close approximation to my original function f of x. And I can now, I can confidently say that, yes, I can stop here because I'm getting very close approximation to my function. Let's simplify what we have here, simplify these terms. So if I simplify these terms, I can get these 4 terms again, which is approximation to my function. When finding the Taylor series of a polynomial, we don't do any simplification to the right-hand side here. We leave it as it is, like here. In fact, if we were to multiply everything out here, we just get back to the original polynomial. All right, so we leave it as it is. All right, so the question here is, how can we code this in MATLAB? So let's move to MATLAB now and let's start coding this. So as always, we need to start the code with clear all to clear all previously assigned variables, close all, which close all opened plots or figures, and CLC, which clear out the command window here just to declutter your code environment. All right, so let's start first by defining a spatial variable. So here let's go by define a spatial variable that I have. So I'm gonna say it's x. So x here is line space from, I'm gonna say from 10 to 10, and give me 100 points. All right, so this is the left limit, this is the right limit, and this is how many points you need to have in your domain. The more points you have, the smoother your plots will be. All right, now let's define the function. Actually, I'm going to use exactly the same function that we have used in we have explained using the PowerPoint. So it's x cubed minus 10 times x squared, and then I have plus 6. All right. Now, I need to just visualize the function. I need to just see what the function looks like. So I need to plot x, f of x, and then I have x label, which is, this is my x actually, and the y label here is my f of x. Right, so let's run this and let's see the function, just here the exact function without approximation. Here I have the x label. Let's run that again just to complete all the information on the figure. So this is my function as we have seen before. This is how it looks like from -10 to 10, and I want to calculate Taylor series around 3, around this point. All right, okay, so let's first calculate define the first 4 terms of Taylor series around 3. So here, calculate the first 4 Taylor series. We have calculated all of them, so I'm gonna just write them right away. So it's -57 if you remember. But in order to plot this, if we want to plot this, I need to make the dimensions of this very similar to the dimension of my function. So I need to multiply it here by a vector of 1s, and this vector has a size of f of x to the second dimension of the function. All right, so this is the first one. The second one is -33 times x minus 3. That's the second term. All right, third term, it's minus x minus 3, and that is squared. The fourth, let's put this capital. The fourth term now is x minus 3, and it's cubed. All right, I'm gonna say an approx here, which is an approximate, the approximate function is ts1 plus ts2 plus ts3 plus ts4, and that is the approximate function. So actually this is the first Taylor series term, and that's the second, and that's the third, and that's the fourth term of the Taylor series, and that is the approximate function. All right, now to just see how it looks like here on the figure, let's add a hold on here so we can plot the approximates on the figure itself. So if I want to say, let's plot the first term. So I want to see the first term actually, and then I want to see the first term plus the second term, and I want to see the first term plus the second term plus the third term, and I also want to see the approximate, which is, so this is approx, which is it's a capital here, which is the sum of the four terms. Maybe I need to put a legend here. So the legend here, I will say the first one is my function actually, f of x. The second one is one term. I only have one term, and the second one I have 2 terms, and then I have 3 terms, and then I have 4 terms. All right, hopefully it works now. So let's run this, and okay, so I have a legend here, legend. And by the way, maybe we can, so here, let's put this as k in black. Here I put B, which is blue but dashed. Here I put red but also dashed. And here I put maybe green and dashed. However, the approximate, I'll use actually magenta, which is very similar to the PowerPoint we had before. And then let's see what we have. I can't write legend. Okay, legend. All right, let's run that. Hopefully it's spelled right now. Okay, good. So if we look here, we can see that the black one, which I can't see it actually. So the black one is f of x, and this is the blue one, which is just one term, the line, and then you have two terms, the green one, and then you have two terms is the red one, and then you have three terms, which is the green, and then you have the magenta one, which very close approximation. All right, so it's very similar to any other function actually you choose. You just need to choose the spatial variable you have, calculate the terms of your Taylor series, and just see where you need to truncate, see where you need to stop in order for you to have a very approximate function. That's it for Taylor series. As usual, I'm gonna add the GitHub link below in the description box, so you can go and look for the code and use it and use it anywhere you like. And if you have a different way of coding this, please let me know in the comment section. That's it for today. Thank you very much, and I'll see you in the next video.